Sorry.
What are we gonna use?
So we're gonna be using for the experiment. We're gonna be using baking soda, vinegar, a cork, and any bottles if you have any, and a few plastic cups.
Okay.
Yeah, if you were not able to collect them, Keenan, Somil, and Arya, or sorry, Somil, to answer your question, are we making a rocket? Yes, sort of. And to answer your question, Arya and Keenan, if you weren't able to collect the kits, you can maybe use them if you have these materials at home. It's just some pretty basic household items, just a plastic bottle or even a glass bottle works fine. A cork and baking soda and vinegar.
So in your kits, you should have the cups and the cork, but from home, we're gonna need the baking soda and vinegar.
Right. And it is 10:34, so I think at 10:35, or you know, I think we can get started now because I think this is everyone. Abdullah, is this everyone?
We can get started. I think a few can trickle in. We can get started now.
Okay, perfect. So, hello everyone. Welcome to the day 4 of the Innovire March break camp slash workshop. Today we're going to be focusing on space and rocketry. More of a focus on rocketry, looking at how rockets work and specifically focusing on propulsion and rocket engines. So I hope you guys get nice and excited. And if you can see here, we have a very special speaker today. Her name is Megan Gran, and she's a 4th-year space engineering student at York University's Lausanne School of Engineering. She built her first robot when she was 10 years old, and since then she's won 2 medals at the Canada-wide Science Fair. She's judged the fair, and she's built and launched a rocket with the European Space Agency in Norway. And on top of that, she's also studied dark matter with the University of Goethe in Frankfurt, Germany. She loves the outdoors, and she goes hiking almost every other weekend in the summertime. And she's also the mother of 2 adorable rescue cats, Pepper and Trixie. So everyone, would you please give a warm welcome to Megan Gran, who will be giving us a presentation about rocketry.
Thank you for that introduction. I will be, am I able to share my screen?
You should be able to share your screen.
At the moment, it tells me I'm not able to.
Okay, we'll fix that for you.
Try now. I think it should work now.
Perfect, it works now. Okay, I will share this screen and I will hit present. There we go. Okay, so I am, of course, Megan
It looks
Gran.
frozen. I think your screen's frozen.
Oh, here. Wait a second. Let me try. Oh, I see. I think I was sharing the wrong screen. Does that work?
Yeah, now
Can you guys
it's
see?
better.
Okay, so perfect. So yeah, my name is Megan Gran, and I am a 4th-year space engineering student at the Lausanne School of University, as was mentioned. And yeah, so I started getting into robotics when I was around 10 or 11 years old. So my elementary school started with Lego Mindstorm robotics. So at the time we weren't competing or anything like that, but we were just building them for fun and playing around with them. And that's how I first got introduced to robotics. Then in grade 7, when I was around 12, I started to compete in the Canada-wide Science Fair. So in the top left image is actually me with my very first robot that I ever built. It was a line following robot intended to take the garbage to the end of a driveway following a line. So I built that robot and then I ended up medaling bronze at the Canada-wide Science Fair. And then in grade 12, in 2017, I ended up going back to the Canada-wide Science Fair again with like a bigger, better, newer version of this line following robot. I actually built it to full scale and I medaled again. And then as well, I've heard a number of you might be familiar with FIRST Robotics. So as well, I participated in first robotics all throughout high school. And I worked on the electrical team and was the captain of the team and part of the drive team. So those were kind of like my introductions to how I got to where I am today. And so also in 2019, I was one of 24 in the uh, throughout Europe and Canada to be selected to launch a rocket in Norway, which was like an amazing, like once in a lifetime experience. So we basically spent the week building a sounding rocket. So it's just a science rocket that stays within the atmosphere and we measured all different kinds of things about the lower atmosphere and weather and things like that. And it was a lot of fun. Yeah, so I was also a co-op student, so I worked at KPM Power, so I was building high voltage electrical systems. I also studied dark matter last summer. I also like to talk about the fact that I have ADHD and anxiety. I know a lot of young people can relate to that, and I think it's important to mention that struggle and realize that you are still able to succeed with these struggles as long as you're able to manage them. And as well, I do have two cats, Pepper and Trixie. Pepper's the white one, and Trixie's the other one. And you might be able to actually hear her scream in the background. So now, a big question that I get all the time, what's the difference between space engineering and aerospace engineering? So the biggest difference is that aerospace is usually within the environment of the atmosphere. So in aerospace, you're dealing with things like fluids. So air is actually considered a fluid because in the way you're considering its movement and its interaction with different bodies. So, for example, airplanes, you have to think about how the air is going to move around the airplane, and that is a huge component of getting airplanes to fly. So that's something you would deal with in aerospace. Meanwhile, in space engineering, the concepts are very similar to mechatronics and systems engineering degrees. So in this, we kind of learn a little bit of everything, and then we take a number of specialized classes and learn about the applications of all these different engineering concepts in a space environment. So we'll learn a lot of orbital mechanics, a lot of space science, and then we learn about how all these different engineering components, how electrical components will function in the space environment, how mechanical components will function in the space environment, and software that's specially used for the space environment and space components. So now, an introduction to rocketry and propulsion, literally rocket science. You guys are learning actual rocket science right now, and you guys are going to leave today being actual rocket scientists. So, the basics of rocket science, I think a huge foundation of it is Newton's laws. So, we have his three laws. The law of inertia, that is when a body is in motion, it will stay in motion unless acted upon by an outside force. So, that means when something is traveling, this law is assumed that it's in a vacuum. So basically, if something is moving, it will move forever and ever and ever. Now, why in the real world doesn't that seem to be true? Why, when you roll a ball on across a table, why will it stop eventually? Because that acting force that is acting upon it is friction, and friction is what is preventing it from continuing. So that is a really important part of rocketry because we have to consider all of the forces acting on the rocket. We have to consider any kind of wind, even friction from the air, and the surface area of the rocket that will cause more drag on the rocket. But we'll get into more of that later. Newton's second law, force equals mass times acceleration. This is a huge component of basically the basics of everything, essentially, in how the world works. So, but in terms of rocketry, this is how we'll be determining how much fuel we need in terms of getting the rocket to lift up based off of its mass. And based off of the gravitational acceleration of the Earth, which, fun fact, is 9.81 meters per second squared. That's the rate at which we are being pulled down to Earth and why we are able to stand and exist on Earth without floating out into the universe. And as well, Newton's third law, which is huge in rocket propulsion, is every action has an equal and opposite reaction. So again, we'll get into this deeper in a little bit, but rockets are basically just combustion within a container. And when you have that combustion, it's essentially like an explosion, but that explosion needs to exit somehow. And so when so when you create a reaction, a chemical reaction, the equal and opposite reaction is what's going to be propelling a rocket into space or into the atmosphere, wherever you want it to go. It's just about the mechanics of designing something that'll direct that energy in the way that you want to use it. So first, I have a video that I thought was cool that shows the way a rocket will be reacting as it's flying through the atmosphere. So how wind will impact a rocket. And I think this is a good introduction to, I'll be talking about the forces that rockets experience within the atmosphere.
Wait, one sec. I just have a question.
Sure.
So these things that you told us are the basics of rocket science?
Yeah, I think they are I would say the base, like they're the foundation, I guess, is a better word.
Oh no, so there's more stuff to it?
Oh my God.
At the rocket this way, it's going to end up tipping like this, and it's going to try to go into the wind to go at the path of least resistance, because this way, there's only this much surface area. Like the very, very tip point of the pen is the only surface area that is going to be facing the wind. So there's going to be the less surface area there is touching the wind, the less force there will be on it. And then force equals mass times acceleration. That's how we get back to that law. So this is a little bit of a diagram. These are both two very similar diagrams, but I like them both in terms of talking about the rocket. But yeah, as you can see, I'm not sure if you guys can see my cursor on the screen.
Yes, we can.
We can.
Okay, perfect. So in terms of the rocket, so if this is okay, so think of the first law. So every force has an equal and opposite reaction. So looking at all these arrows here, so this is the flight path, and this is the direction that the rocket is going, and then this is the like the energy coming out the bottom of the rocket to be able to fire it into space. And these three arrows here, the drag, the transverse force, and the lift, those are all reaction forces. And I guess technically the actual force is a reaction force from the combustion inside the engine. And but that's the application of that first law. So these are all reaction forces. So these are all needing to be considered when designing a rocket and designing where you want the trajectory to go, because you can't just launch a rocket and not know where it's going to end up. You have to know, yeah, you have to plan where it's going to be, and you probably have an intent of where it's going to go. So you have to consider that lift is going to occur from the wind. So this is something that is more aerodynamics. Well, of course, this diagram says the aerodynamic forces acting on a rocket, where basically when the wind is facing and coming at a rocket, it's going to catch into the wind, and the wind is going to like scoop it upwards. So the same way when you're in a plane and the plane tips upwards, and then all of a sudden you're lifted up off the ground, that's basically going to happen on a smaller scale with a rocket. So yeah, just think of like the wing of a plane in terms of that. And then the drag, like I said, the drag is the wind causing, essentially wind friction is the easiest way to think about it. So the more space you have touching wind in on like the sides of the rocket, the more drag you're going to have. Think of a sailboat. So a sailboat has a huge, gigantic sheet, and it's being pulled on by the wind, and that is how the sailboats are being propelled, is from that drag force. And so in rocketry, you don't want drag force, or you want minimal drag force. That's why the rockets are very small, very skinny, if needed be. Of course, there's other like larger rockets, but usually that's because they have a giant payload. And but yeah, this is another diagram of that as well. The D is representing the drag force, and then mg is called the center of pressure. So that mg represents just mass times gravity, is that downwards force. So the downwards force on the rocket is its mass in kilograms times that 9.81 meters per second squared, the downwards acceleration of gravity. And basically, the minimum force to get the rocket to get off of the ground, assuming no other forces are acting on the rocket, is going to be what this value is here. Its mass times its gravity. And that way it can, yeah, that is the minimum force needed to lift that rocket off of the ground. And yeah, this is the center of gravity and center of pressure. The center of pressure needs to be ahead of the center of gravity, otherwise the rocket will end up spinning like this. There's different types of software and methods that can be used to find the center of gravity and the center of pressure, but typically the center of pressure is where you're able to get the object to, I can't get it to balance, but it's where you're able to get the object to balance, like this. This would be where this center of pressure is, approximately. Okay, so now what is a rocket? So, according to Google, a rocket is a cylindrical projectile that can be propelled to a great height or distance by the combustion of its contents, typically used as a firework or as a signal. So yeah, a rocket is just a projectile and has some kind of payload and has some kind of propellant. So this, we won't worry too much about this right now, but I like to introduce it, not to scare you guys, but this is the rocket equation. So this is a lot of the different components of rocketry relate back to this equation. But don't worry, there's a lot of software these days that's used to calculate all this stuff. So you don't have to, you know, you don't have to pull out your calculator or anything like that. Unless you take it for school, like me, then unfortunately you're going to have to do a lot of this, but it's not that scary, trust me. So yeah, so basically these are all the different things that are considered when considering rocketry. So delta V. So delta means the change in. It's just delta is just a, sorry?
Delta is the fourth letter of Delta's the fourth letter of the Greek alphabet.
Exactly. And so that Greek alphabet letter is representative of the phrase change in. So that is that triangle there in front of the V. So delta V.
I know. And the lowercase form is the circle with the thingy that looks like a G, the tail of a G.
Exactly. Oh, that's awesome. You're ahead of the game. Okay, so this is the maximum change in velocity of the vehicle. So this is essentially the maximum velocity, so the fastest this rocket will ever go, minus the slowest it'll ever go, which is usually 0. And then we have the total initial mass and the total final mass. So that's important to consider because when think of like the gas in your car. When you're driving in a car, you end up using up the gas in the car. And it's the same with rockets. To be able to get the rockets to move, they have to be using up this gas. And using up the gas means that there will be a change in mass. And a change in mass can impact the way the rocket moves. It'll actually impact the center of gravity and of pressure. So think of the center of pressure is where I got it to balance on my finger. If I have a bunch of fuel back here and all of a sudden it disappears, that center of pressure is going to end up changing. So that's why that's important to consider in the rocket equation. We have the exhaust velocity. So velocity is just another word for speed. So exhaust velocity is just how fast we're getting rid of the gas. So then you can estimate over time, how much the weight of the rocket is changing. And then there's the logarithm function, which is just the function required to manipulate these numbers. So yeah, so a bunch of important components of a rocket. This isn't all of them, but these are just some notable ones. There's motors, there's the nozzle, there's the nose cone, there's fuel, there's payload, igniters, and lots more. I'll be getting into a number of these in my presentation here. So this, does anyone know what this part of the rocket is?
The nozzle or the cone?
Yes, it's the nose cone, exactly. So this is the very top of the rocket. So on the left, so this is actually my friend's rocket. My friend built this, and she showed it to me the other day. And so this on the left is one of the earlier designs of the nose cone, and you can't really tell in the photo, but this nose cone was very rough. It felt like sandpaper. Like it did not feel smooth, and it was very heavy. Now the one on the right, it was like perfectly smooth, and then even the very top of the nose cone here, it was also perfectly smooth. That top is made of metal, and then this body part is made of fiberglass. It's really important for a nose cone to be extremely smooth because if it has um, anything that has any kind of holes or any kind of bumps, like even these here are what they call parasites. So essentially, they're little things where air is going to latch on when it's going at high velocities. It's going to change the airflow around the rocket as well as slow it down and make
And I
it.
think for the rocket to make it to space itself, that nose cone needs to be really like smooth and pointy at the top, because
Mhm.
that's how it's gonna cut through the air.
Exactly. Yeah, and we need to be able to predict how it's going to um, interact with the air that it's moving through as well. So if there's any kind of, like if it's not perfectly symmetrical, for example, then it might lean to one way when it's going through the air, which it may not be expected if you're unaware of the way that it's leaning. So yeah, so this is the diagram that I showed earlier of all the different components of the rocket. So yeah, the top is the nose cone. The experiment, that's just, I think, just another word for payload, essentially, where you would put maybe sensors or um, maybe you want to test how a material would act in a inside of a rocket. So you want to see how it would handle the pressure changes of going upwards towards space. That's where you would put those kind of things. And then it has a bunch of other sensors here. So radar tracking beacon, that's just another word essentially for, a GPS sensor. And then the telemetry antenna. So this is the antenna that is going to be um, communicating the information on the rocket back to what they call a ground station. So that's just basically where the information is received. So just a big satellite dish that's going to be watching for this rocket in particular and trying to receive the data. And then recovery in airplanes, they have something called a black box, where basically, I guess a simple way to put it is like a little USB stick with everything that the rocket recorded. So basically, when you find this rocket again, you'll have that little info drive of everything that the rocket recorded. That's in case the telemetry antenna doesn't transmit the data during the launch, in case something goes wrong. And then They have something called D-spin, so as a rocket goes up, it's naturally going to turn in space, like on its own axis, like this. And sometimes they don't want that, so they actually have something that will let the back of the rocket rotate instead, so then the rest of the rocket can be moving straight forward, but only the back end of the rocket is twisting. And then, of course, we have the rocket motor. This is where the fuel is, where all of the explosions and combustion inside the rocket happen that let it launch forward. So I have another cool video here.
Now let's take a look at this test in slow motion. Standing by for ignition. Actions to click the boost phase. Now we're seeing the sustainer phase to burn. This rocket motor only burns about 1.2 seconds. Now this is the smoke tracking charge, where C65 rocket motor is charged.
So basically, that was a rocket motor that was ignited with fuel. And I have another video here of one.
Extended to various lengths away from the nozzle exit.
So if you see that little, this little thing here, this is the igniter. So that is essentially a little resistor that they give a voltage to, and then it ends up sparking. And so that little spark is what ignites the fuel inside of the rocket.
It's extended to various lengths away from.
So now let's talk a little bit about the propellants. So there's different types of propellants that'll make the rocket react like it did in those videos. So there's liquid and solid. So what are the benefits of liquid and when would you use liquid? So liquid is considered to be a more professional and complex fuel for rockets. So in liquid fueling, you're able to control how much fuel is actually being output. So once you ignite the rocket, you are able to control and, well, you're able to have controls where you could stop the fuel from igniting, or you could inject a lot more fuel all at once if you want the rocket to have a lot more thrust. And the different types of fuel, there's liquid oxygen, you could just use alcohol or gasoline, and they could also gel them, so that's where it would literally just turning the fuel, so think of like gasoline turned to a gelatin, like a jelly, and then that way there's a less complex system required and it acts more like a solid fuel. But yeah, overall liquid fuel, you need a lot of components. You need the injectors and all different kinds of components to be able to control it more, but you do have way more control with it. Solid fuel is something that's used in a lot of model rockets, and one of the common solid fuels in model rockets is a version of paraffin wax, actually. And it's essentially just a chamber and a nozzle. The only downsides of these is once it's lit, you cannot stop it because it's a solid and it's going to burn all at once. You can't, remove any kind of the solid. Like once it's burning, the whole thing is going to continue to burn. It is easier to control in a sense that there is less components and that it's more consistent in the way it's going to react. And the other benefit of it is that since it's not a liquid, it's not going to be sloshing around in the rocket in any way. which is also considered to be a benefit. But yeah, so thinking back to the foundations and the laws that we applied earlier, and also the what we saw in those videos of the rockets igniting. So basically, here, this is a rocket nozzle. So this is what is inside the base of a rocket. So that is at the very bottom of the rocket here. So this part of it here is what is on the very, very bottom, the exiting part, and then this container is a little bit higher up in the body of the rocket. So basically what happens is once this fuel is ignited, there's all this energy being trapped inside of this container. And it ends up building up a ton of gas, a ton of pressure, and because it's a chemical reaction. And that needs a way to exit. Otherwise, it's going to just explode itself. So, what they have here, they have this thinner part of the nozzle that is used to assist in directing and accelerating all of the pressure that is inside of the combustion chamber. So think of, have you ever had like a garden hose and then you like stick your finger in the garden hose and so you're able to make the water shoot out farther or faster? This is essentially the same concept. So that when you stick your finger in the garden hose to make the water come out faster, you are like limiting the exit route that the water has. So that will increase the pressure, and that is what increases the velocity of water exiting the garden hose. It's the same concept here. So that thinner part is meant to increase the pressure, increase the velocity of the gases coming out of the rocket, which is what is going to accelerate and propel the rocket towards space. Yeah. And yeah, I guess I have my video of my rocket launch here. So that was my rocket, but I'll go step by step and I'll explain some of the parts. So was the sound still not working?
Not really. It was really low
We
volume.
could hear you through your own mic.
Increase your volume.
Oh, okay, okay.
If you were to exit the share screen and then check the share sound button, then we'll be able to hear the sound this time around.
Okay, I will try that.
So when you're on
Uh,
the share screen tab and you're selecting the window that you want to share, there should be in the bottom left corner of that screen, there should be like a share sound icon.
yes, okay,
Yeah, so
perfect.
if you check that off now, we should be able to hear your sound.
Okay, amazing. So I just checked that off, so it should work now. But basically, you'll hear a countdown in this video, and you'll hear the countdown, and then you'll hear them start to count up after they hit zero. So they'll say 5, 4, 3, 2, 1, 0, 1, 2, 3, and I'll show you that, and then I'll explain why that happens.
7, 6, 5, 4, 3, 2, 1, fire. 1, 2, 3.
So if you saw back there, the rocket actually only launched 3 seconds after he had already said zero. So that occurred because this rocket that we used was a solid rocket. And with the solid fuel takes a longer amount of time to ignite because it's a solid. Think of when you're lighting well, hopefully you don't like gasoline. But if you've ever seen videos, I see people laughing there. But yeah, if you've ever seen videos of gasoline igniting, it catches right away and it goes very, very quickly and very, very fast. But then think of like when trying to
So
start a
you
campfire, or if
could
you've seen videos of campfires, when trying to light wood on fire, it takes a long time. Like you have to really sit there with a match and kind of wait for even just a twig to ignite. It's the same concept with liquid ignite way faster than any kind of solid fuel. Um, and so that's why there's that little gap in the timing there. And then I'll also show you. So in this portion of the video, watch this big white thing in the top right corner here as the rocket moves. So if you saw that, this thing, it moved and followed the rocket. So remember a few slides ago where I was talking about antennas. Yeah, so the telemetry antenna. So that big white thing that was moving, that was the receiving antenna for the rocket. So that is why it was following the rocket directly, because it's trying to receive the rocket signals as it's moving through the atmosphere, so then we can get its data from it. So that was that portion of the launch. I just thought that was interesting to share. And then yeah, and then I guess I kind of want to leave off with, how can you learn more about rockets and rocket science from home? So a lot of the YouTube videos that I shared were from Lab Rat Scientific on YouTube and PBS Space on YouTube. There's also different, these are some textbooks that I got my information from, but textbooks are a little harder to get. But, YouTube is free. So yeah, definitely look up rocketry from YouTube as well. There's something called Open Rocket, which is a free software. I haven't used it before, but it is a free software. Hold on. Yeah, OpenRocket is a free software. And also, there's actually a game on Steam, and I have this game. It's very hard, actually, but it's called Kerbal Space Program. And you essentially get to build rockets. But a lot of the physics and mechanics of this game are fairly accurate. So if you want to get like practice virtually building and simulating your own rockets, put that on your Steam wish list. Wait till you get that on sale email. And it's genuinely like a really great game if you're interested in rockets as well. NASA, ESA, the Canadian Space Agency, Launch Canada, and Google Scholar are all other really good resources and read up on rocketry. In terms of Google Scholar, just look up Google Scholar and it'll basically come up with a new Google search menu. And you're able to search up like rocketry, for example, but you get scholarly documents. So they're documents that are from like professors and scientists and like published materials, not news articles and things like that. So you'll get introduced to a lot more of the technical terms and things like that. But other than that, that is my presentation. And thank you guys for listening. And I'm totally open to questions. And yeah, feel free to ask questions.
Thank you very much, Megan. That was a great presentation. Kerbal Space Program is actually a really fun game. I highly recommend it. I've played it too. It's really fun and also really satisfying. But there's so many people that left questions in the chat, so I'm just gonna open it up.
Oh, okay.
We'll start with Abrar. You can go first.
So are there nuclear rockets?
Sorry?
Are there nuclear rockets?
Are there...
Your mic quality is not great. If you could type it in the chat, then maybe we'll just be able to read it out.
I was asking, are there nuclear rockets?
I am not 100. I'm gonna say probably yes, because there's because there is. I would say probably yes, but I can't think of any rockets that use nuclear power at the moment, and I'm sure it's probably very dangerous and difficult. So I don't know if it's actively in use, but I'm sure it's being studied.
It is a work in progress. Yeah, nuclear powered rockets they're being researched at the moment. Abrar just went. Gursahaj,
I have a question. So, like, when the rocket goes to space, would it eventually loses its weight as it's going away from the center of mass of the Earth?
Sorry, can you say that question one more time? I think my computer froze.
Okay, so when the Earth goes to space, would it eventually lose some of its weight as its distance from its center of mass will from the center of mass of the Earth, like it's going away, like further, more further?
Traveling through space with that combustion in the engine of with that chemical reaction occurring, it is going to be losing the mass of the fuel is going to be the main loss of mass. There are other ways it could lose mass if, like parts fall off or things are burning up or degrading as it goes through the atmosphere, but that's typically on a much lower scale. But yeah, the biggest mass loss is going to be the fuel being lost.
There's also in Newton's laws of gravity, this formula, like if you go more away from a center of mass, its gravitational force, like more it's less, and therefore its weight sometimes gets less.
Oh, so I think I see what you're asking or what you're saying now. So the thing is, mass does not change in regards to gravity. The mass will always stay the same, except the mass is changing because we are losing the fuel. The weight, however, you're correct, the weight will be different as it gets farther from the center of the Earth and as it goes in towards the atmosphere. So weight is something that is a relative measure. So weight is different pretty much anywhere in the atmosphere and anywhere in the universe. So on the moon, you're going to weigh differently than you would on Earth, except our measure of weight is based off of that gravitational acceleration constant that I had mentioned earlier, 9.81 meters per second squared. So that is the mass times the acceleration. But the mass part never changes unless you're actually physically losing components, as you would like losing fuel.
Red Mars, you can go ahead with your question.
Okay, what is the difference between the center of pressure and the center of gravity?
So center of gravity is essentially it's a bit of a complex thing, and I would definitely encourage you to watch some YouTube videos after because I don't know if I'll be able to give like a really good explanation, but that's a really good question. The center of gravity is in terms of the mass distribution of the thing that you're talking about. So of the rocket that you're considering, that would be the center of gravity is the way the mass is distributed. And then from my understanding, the center of pressure is essentially the point of balance on the rocket. I can't give like a super clear in-depth explanation because I it's a complex topic, but the center of gravity usually doesn't move on a rocket, but as a rocket is launched, the center of pressure will change.
I think
Related to the environment. And Arya, do you have a question?
how do you control how much fuel exits the rocket? So if you want to conserve fuel if you get into space, how do you save it?
So you wouldn't be able to save it with a solid fuel, so that is why you would use a liquid fuel. So a lot of the SpaceX launches that you see, or the NASA that you see, a lot of them use liquid fuel, and they have something called injectors. So that's how they can know how much fuel already calculated ahead of time. Okay, we need this much to get out of the atmosphere, and then we're going to need this much fuel to, for example, get from the space to, like, let's say the moon. They've already done all those calculations. So what they can do is inject only the amount of fuel that's required for that stage of the rocket. And then, when that's also why they have rocket stages. So normally, once they use up a stage, that's usually because they get through a specific phase of the environment they're getting through. So they'll have one stage for within the Earth's atmosphere, and then they'll drop that stage because it's just dead weight at that point. It used to hold fuel, but now all that fuel's been expelled to get to that portion. So they'll get rid of that stage, and that's why they have another stage, because that next stage will be used to travel, for example, from the atmosphere to the moon. And then when that's done, they'll drop that stage again because it's run out of fuel. So yeah, they can either use stages or different levels of injection of fuel.
Okay,
So they can
thank
create
you.
like different portions of the rocket to like complete different phases.
Yeah,
And then
exactly.
when one portion is all used up, it just falls off or something.
Yeah, exactly. So it's like having multiple gas tanks.
Oh.
Mhm.
That's a good way to think about it, having multiple gas tanks. I see Keenan, you have your hand up.
Oh yeah, so my main question is, what is rocket fuel made out of?
It could be made out of a lot of different things. So I have back here, rocket fuels, liquid rocket fuels could be made out of liquid oxygen. It could be made out of alcohol, it could be made of gasoline, and then in terms of solid fuel could actually be made from paraffin wax. You could also actually make fuel from sugar. It's basically anything that will is considered a fuel. So even wood is considered a fuel. Think of like fire burning that involves combustion and fuel burning. Yeah, so anything that can combust and anything that can create energy could be used as a fuel. But yeah, these are the typical ones.
Okay, thank you.
No worries.
Arnav?
Are scientists trying to make like a plant-based gasoline for like plant-based rocket fuel?
So actually, there are a lot of different types of fuels that are plant-based. So like I said, sugar can be used as a rocket fuel. So technically that's like a plant-based fuel. Um, in terms of like on a commercial scale based, I would assume not. But I'm not sure of any pushes to use strictly plant-based fuel instead of fossil fuels.
Oh,
Um,
because I thought like because people are using like canola, for example, to make diesel.
oh, okay. Yeah, I'm sure there's a push for it somewhere, but I don't know if it's at the forefront because in terms of like when they're putting people up into space, I know they're very sensitive about um, making a lot of major changes like that, like the type of fuel. But I'm sure it is being studied somewhere.
Okay.
Arya and Red Mars, are these new questions or are these like, did you just forget to pose your
Yeah, I
question?
have another question.
Okay, yeah, please go ahead.
How do they keep the rocket fuel, if it's a liquid propellant, how do they keep the rocket fuel at the bottom of the tanks? Like, after don't have any gravity, won't the rocket fuel just float around in the tank once it's like half empty?
So that's a really good question. So there is a video that I watched on this recently on how the it combusts. But basically, since it's happening so fast, and the tanks are usually highly compressed. So think of when you fill up a water bottle, like all the way to the top. When you rotate it, there's not going to be any kind of air bubbles in there, and when you shake it, it's not going to move around, right? It's only going to stay together. So that's how they fill it. And then when it's igniting, usually it ignites from the point of, like, let's say this is a rocket nozzle because it actually kind of looks like one because it's smaller at the base here. When it ignites, it's going to just move up um, the tank as it's exiting, but you're going to get the most thrust at the very beginning. But since it's igniting so quickly, it moving around, it isn't usually that like big of a concern from my knowledge, or at least my uh, the kind of rocketry that I've worked with. But yeah, it just usually goes so quickly that it's not too much of a concern.
What I mean is like not it sloshing around, like after you're in like no longer affected by the pull of gravity, how do they keep the fuel at the bottom of the tank where the injectors are or the fuel pumps?
So in that case, it since the ignition is still happening within the tank, the it doesn't actually have to be at the very end of the tank. So when this combustion is happening, there's gas that's being um, produced from this reaction, and that gas is building up pressure. And so when you have this smaller nozzle here, it is able to push out gas. And so it doesn't necessarily have to be at the very end of the nozzle because the pressure is coming from completely within the bottle or within the tank. So it's the gas that is causing the force to be exited out, so it doesn't have to be at very close to the nozzle because the pressure is all being created all within the tank, if that makes sense.
Okay, thank you.
So if that's the end, if anybody else, any last minute questions, do feel free to ask. But I don't see any hands, so I think that that's it for the questions. So that was really good active participation, and I think I speak on behalf of all of us when I say that was a really good presentation, really educational, and there's some things that I think all of us are able to learn and take away from. So thank you so much, Miss Grant, for that amazing presentation. And I believe it is like 11:30 now, so I think you might have to go. So everyone, please do again give some applause for Megan Grand, who gave us an awesome presentation, and we're gonna move on now. So
Thank you very much. You guys all had really awesome questions. Feel free to reach out to me or connect with me on LinkedIn if you have more questions. And yeah, use those resources to study rocket science. And yeah, be a rocket scientist with me. It's a lot of fun. But yeah, enjoy the rest of your presentation and the rest of your labs and the rest of your day. And thank you for inviting me.
of course, and you too enjoy the rest of your day.
Thank you.
Bye.
Bye.
Bye-bye.
Goodbye.
Goodbye.
So now we have about 30 minutes till our break. So what I want to do is I'm going to be sharing a little presentation with you guys now, just not as long, but this is going to basically outline the science and what we're going to be doing in the activity, which will happen directly after the break. So after the break, I want you guys to have all your materials ready and just get ready to make this baking soda engine. So I'm going to go ahead and I'm going to share this. Okay, so can everybody see my screen?
Yes.
Okay, awesome. So we're gonna keep this just like the last presentation. If you have any questions, do feel free to unmute and interrupt me at any time. But we're just gonna be looking at using baking soda and vinegar to make our own rocket. So due to some restrictions, we're not gonna be making a rocket today, but we are gonna be making an engine. Okay, so so this is an introduction. So this is sort of on the bottom here. This is what it'll look like. That I used a glass bottle, but I think most of you will be using plastic bottles. But again, it doesn't really matter what you use. So just to review the last session, we learned about how propulsion works, how rocket engines work, and how rockets work, and all the different physics principles that go into it. And now we're going to explore kind of the hands-on aspect, so how we can make this ourselves. So again, as Megan Grant said, there's a lot of different ways to do this. In fact, you can even use sugar to make your own rocket. But today we're not going to be playing around with fire because that's a little dangerous. So we're going to be using baking soda and vinegar. But there are ways to do this, where you actually get a burn. But this one, we're kind of going to be using this cork to kind of visualize the fuel. And this whole bottle right here is our engine. And the results are pretty spectacular, I'll tell you that much for sure. So just to review how a rocket engine works, so it shoots extremely hot and pressurized gases through the nozzle, and due to Newton's third law of motion and the conservation of momentum principle, this causes the force thrust which propels the rocket. So we're going to be making this engine that can produce the thrust. So we're going to be making the thrust aspect, we're just not going to be seeing the rocket move. Again, this is due to all these different restraints and all that stuff. So rocket engines, so they work fairly simple, right? So they have the fuel tanks, the combustion chambers, and the nozzle, right? So we have our fuel tank over here, our oxidizer over here, which again we looked at in the previous lesson, but we have the fuel, the oxidizer, and then we have them both fed into the combustion chamber, which then goes into the nozzle, which will all exit as exhaust at a very, very high speed. So we're going to be looking at it in the same way. So our engine is sort of like a hybrid rocket engine. So a hybrid rocket engine, unlike a liquid engine, will use a combination of a solid fuel and an oxidizer to burn. So over here, if you look on the left, you have this hybrid rocket engine diagram. So over here in the spot of the fuel tank, you actually have a solid fuel grain with passage in the middle. So this basically means that it is a normal cylindrical fuel tank, except the outer layer is coated with some sort of solid fuel, like it might be some sort of sugar mixture or wood or anything or even like a gel of kerosene or any sort of solid fuel. And the middle will have a passageway for the oxidizer, and inside we'll use an igniter or a spark plug, which is just a resistor on the end of a conductive wire to produce a spark, and that'll cause the burn and the nozzle and the exhaust and all the same things. You get the same result, but just in a different way. And the next part is the R engine. So this is a diagram of our engine. So instead of an oxidizer and a fuel, right, we only really have sort of an oxidizer. We don't even have a fuel, right? But if you want to really, spoiler alert. I'm gonna head back. Hold on.
Okay, so I got a good.
Well, this is just outlining kind of the chemical reaction, but that's a little bit of a spoiler alert, but that's fine. But anyway, so the hybrid rocket engine over here. Oh, now it's loaded. Okay, there we go. So the hybrid rocket engine over here that we're making is not really much of a hybrid because we don't have a fuel. We only really have an oxidizer, and our oxidizer is carbon dioxide. So for those of you who don't know, in actual rockets, the oxidizer is used to help the fuel burn because in space there's no oxygen, right? And even if you were on Earth, in order to get a more efficient and focused and forceful burn, you would need some sort of oxidizer. So usually this is in the form of liquid oxygen, but this can also come in the form of liquid hydrogen and liquid carbon dioxide and other liquefied forms of, atmospheric gases. So carbon dioxide is actually a popular one too that's also used. They also use liquid methane and stuff like that. So for our reaction, since we're making this at home, we need to be able to make the easiest one. So the easiest way to do this is to get baking soda and vinegar in order to get the oxidizer of carbon dioxide. So we're going to be exploring this in the next slide, which you guys sort of got a peek at, but this reaction actually produces carbon dioxide, which will act as our main oxidizer. And if you really want to envision a fuel, you can sort of think of the cork as the exhaust or the fuel, because that's what's going to be propelled. That's going to be thrown out of the nozzle. The cork is going to be thrown out of the nozzle. So you can envision that as sort of the fuel. So in this, if you were to put this together as a rocket and not an engine, the cork would be the fuel and the oxidizer would be the carbon dioxide inside the bottle, and the nozzle would be the bottle cap or the bottle opening, and your combustion chamber is essentially whatever's going on inside your bottle. So now we're going to take a look at the chemical reaction. So over the past, I want to say couple days, you guys have been looking at some chemistry. Not couple days, sorry. I think that was on Tuesday. You guys looked at some chemistry. So we're going to be bringing back all of that chemistry knowledge in a simple chemical reaction to figure out how our rocket works. So this chemical reaction consists of two things, so baking soda and vinegar. But if you want to get all fancy, you can call baking soda sodium bicarbonate, which is what it is, which is essentially just sodium and a polyatomic ion called bicarbonate. And then you also have ethanoic acid, which is just vinegar in fancy terms. So vinegar is just a little bit of, I think 5 to 8% of ethanoic acid dissolved in water. That's all it is. But it's really strong. Just that 5 to 8% is a lot of concentration, which is why vinegar smells so pungent. You know, it's a really strong compound. So the way this chemical reaction works is that the sodium over here. So this is just, explaining everything. So the sodium, how it works is the sodium bonds with the acetate, which is on the other side. That is your C2H3O2, which is carbon, hydrogen, and oxygen. So when those three, here, you know what? Let me get this highlighting tool for you guys. Oops, I keep playing the video by accident. Again, that's a spoiler alert. We don't want to see that just yet. Turn on the laser pointer. Okay, there we go. So, this right here, the second half of your ethanoic acid, the C2H3O2. So that is all known as acetate. That's a polyatomic compound called acetate. And it dissolves in water. But what happens is in this reaction, the sodium over here bonds with the acetate over here. So the reason they bond, that's a little bit too much chemistry, but if you must know, it's just because they're both ions and the sodium wants the electron that the acetate is able to give. So the acetate gives the sodium the ion and they both bond and they end up dissolving in water together. But those two bond, leaving this over here, which is our bicarbonate, and our hydrogen over here. So this hydrogen over here and this bicarbonate over here, they all want to bond together. So these guys come together and they bond. But they make a really unstable compound called carbonic acid. So what happens to this carbonic acid is that it further breaks down into carbon dioxide and water. So if you look over here, if you combine this HCO3 and this H, then you just get H2CO3, which can be divided into H2O and CO2, which is just H2O. I'm sure all of you know that is water, and CO2 is carbon dioxide. So this is the full chemical reaction written out over here. So what can we conclude? So we can conclude that when you mix baking soda and vinegar, when you see that fizzing, that's actually just, that fizzing is just a result of your carbon dioxide inside your water, and all that bubbling and fizzing up you see is because it's building up that pressure, and that carbon dioxide is causing air bubbles inside of your vinegar and baking soda, like the water that's already there. So that's a rundown of our basic chemical reaction. And in the way that rockets kind of mix, let's say liquid oxygen and kerosene, and they get a chemical reaction that ends up burning and making exhaust, right? In the same way, we're doing the same thing by mixing vinegar and baking soda, but our exhaust is just carbon dioxide. Oh, okay. Oh, there we go. That's nice. Oh, you know what? Actually, let me disengage. Okay, yeah, let me go back to this slide so I can show you guys what the chemical reaction looks like. So if you look at this video over here in the bottom left, you will see. So that's me kind of running a demo of the experiment. But you can see how that the vinegar starts down there. When I put the baking soda, you can see the level of water rise, or the level of the solution. You can see it rise. So it's rising because it is producing water and carbon dioxide that are increasing the water level. So I'm going to let you guys look at that one more time.
Okay, so I got a good.
Yeah, so you can see the water level rise quite significantly. So let's, oops.
Okay, so I got a good.
Okay, let's move on to the fuel. Okay. Oops. Yeah, so as I was, oh, my bad. Just a little bit. Yeah, so looking at the fuel, so as I mentioned earlier, right, our main fuel is sort of the carbon dioxide. You can think of that as fuel, and you can think of the cork as fuel. So these are our two fuels, because every rocket has, an oxidizer and a fuel, which are really, both of them can be considered just two different forms of fuel. But for us, our carbon dioxide is our main fuel, and the cork is our exhaust. So you can think of both of them as fuels, essentially. So the reason why this is important, and this is also over here, I'm just highlighting, this is sort of a diagram. So you can see the atoms and you can see them break down into water, carbon dioxide, and sodium acetate. But the fuel that what happens with this fuel is it's built up inside the bottle, the carbon dioxide, and this is important to us because this is what causes our cork to pop off. So the fuel, when you put the cork on, this causes it to be kept inside the bottle. And when you keep adding more and more carbon dioxide to a limited volume, what happens is that your pressure starts to increase. So you get more and more of that carbon dioxide that wants to escape the bottle, but it's trapped inside. And this causes a lot of pressure. And eventually when this pressure releases, that is what causes the cork to pop off and our engine to work as it does. And that's just, again, that's the chemical reaction, but it's a little bit better view. So move on. Okay, so pressure. So this is actually take a still from the video of the reaction, which I will be showing next. But pressure is really important in this engine. Pressure is, even in any engine actually, pressure is really important because, as Megan Gran explained in her presentation, in a nozzle, when you have that point where the flow is choked at the throat of the nozzle, that's when the dynamic pressure becomes the highest, and that causes the velocity to accelerate a lot. So what happens is that pressure is the motivating factor for the fuel to move. When you have a high pressure inside here and a low pressure outside here, the pressure wants to move outside as fast as it possibly can. So that's what's happening here in this still. So inside the bottle, there's a lot of built up pressure, and all of that sort of foam or fog or steam that you see, that's all the baking soda, vinegar, and carbon dioxide. It's all like, that's it in its vaporous form. So there's so much pressure built up that as it releases, you can actually see the pressure release in the form of this gas. But there's a lot of pressure inside the bottle, and outside the bottle, there's just atmospheric pressure. So it's not a lot of pressure compared to inside the bottle. So what does pressure want to do? It wants to move from highest to lowest. So the high pressure inside the bottle wants to move into the outside atmosphere. And that's what causes this boom, this gigantic pop. Okay, so now we know all the different components, so let's just review, how does our engine work? So our engine works by building up enough pressure inside the bottle using our cork so that the force exerted on the cork allows it to be blasted off. And that acts like the fuel in rockets, and that produces thrust. Now, if you actually see in the video and in the experiments when we run them, the bottle is actually going to move back. When the cork pops off, the bottle is going to move back. This is because there's nothing holding the bottle in place, right? So it's Newton's third law. For every action, there's an equal and opposite reaction. So with equal magnitude but in opposite direction, the bottle is going to move back because of the force acting in the opposite direction. So the chemical reaction that occurs allows our pressure to be built up, and the pressure is what allows the cork to be popped off. Okay, so this is construction. So we're going to review this after. That's just a short little thing about.
Okay, so in order to make,
that's sort of just like how I built certain parts for the rocket. But what I want you guys to see is this. Okay, so this is the experiment. So, while it loads in, we're gonna go full screen on this one.
So now we still have some vinegar.
Can you guys hear
and
it?
some baking soda. So there's nothing wrong with you reusing this. So I'm gonna.
Okay, perfect. Okay, so this is, yeah.
I'm gonna try again. So this is attempt number 2.
So that is just a really cool, that's what your experiment's gonna look like. So the only thing that I did is I kind of used a little bit too much of baking soda and vinegar. So that's what caused the reaction to be so violent. If you saw the cork, it flew it flew super far, and there was a
So
loud
now we still
noise,
have some
and everything backed up,
So
and
now we still-
there was a bunch of baking soda and vinegar everywhere. So I used a little bit too much vinegar and baking soda. So I would advise you guys to use a little bit less. But overall, like, yeah, that's sort of what happened. So let's analyze like what's right. So the rocket worked nominally. So the word nominal means that it worked as it was supposed to. So I want you guys to know that there's no right or wrong when you run this experiment. However your rocket works, it's all just based on however you wanted it to work. So the baking soda and vinegar reacted, and as you saw, there was a lot of fizzing inside the bottle, which is that carbon dioxide being produced, and you could see that when that pressure was released, you saw the vapors go out, and you saw that there was a lot of pressure built up inside, which caused there to be an overall larger force, which caused the cork to move so fast and so aggressively. And I'm sure you guys heard that huge sound, which sounded like an explosion, and that flew right into the cups. So now I'm just gonna explain the procedure before we head out for lunch in another 10 minutes or so. So here I have these cups. So I put them back there to collect the bottle and the cork. These didn't work really well because mine was so violent that the cork just launched right through. It absolutely destroyed the cups. And the bottle that launched backwards also just completely, like, everything was just all over the place. Nothing broke, thankfully. And it's not an unsafe experiment, by the way. I just did it in like a really unsafe way. But what you want to do is you want to learn from my mistakes, and you want to use very little vinegar and very little baking soda, which will be enough. And if you keep these cups here, the cork should collect in one of these. Oh, see, that was my cork, actually. This did work. So the cork flew into the cup, and the only thing is it went in with such force that the cork actually like broke it. But this is the cork that I used, and I had just this bottle, so you just kind of pop that in. And if you notice, I had to push my cork in rather deep, because if there's any room for anything to escape, then it won't work, because then the pressure is going to be relieved, but you don't want the pressure to be relieved, you want it to build up inside. So I had these things, which I made simply by taking some cups and taping the bottom to some cardboard. So I made 2 of them so that I could collect the bottle in one and the cork in the other. It's really important that you put this sideways, because if you put it upwards, then you're just gonna, I mean, you can do whatever you want, but it all depends on the mess that you want to clean up. I put this on its side because that way you could kind of see everything in a good angle, and when everything went off, like, it wouldn't make too much of a mess because it was lying down. So you're just gonna need to put some tissue paper underneath your bottle, because when the cork pops off, naturally there is going to be some baking soda and vinegar that spill out. But that is basically how the experiment runs. So if you guys have all your materials, you should get that ready. And if you have any questions, do ask me. Any questions, anyone?
No.
Okay, perfect. So no questions. Okay, so I want you guys to get excited, because right after the break, we're going to be working on these. Oh, did I hear someone say something? Okay, I'm gonna take that as a no. Okay, but anyways, yeah, so we're gonna go on and proceed with our actual experiment. I see a lot of chat messages though, so I'm gonna. Arya asked, okay, hold on. I missed a lot of stuff. So the cap has vanished. Okay, judging by the set. Okay, let's move up a little bit. Okay, NaCHO. Yeah, it's a compound. Yeah, so this is just talking about sodium bicarbonate is, yep, NaCHO. Very good. This is the best chemical. Nacho. Ha, nachos. Yeah, actually, that's true. Nacho. That's the chemical formula. NaCHO. Nachos. That's funny. Will the cork blow off when we mix the mixture? Yeah, so as you saw in the video, once you push the cork in, you give it 2 to 3 seconds maximum, and the cork just explodes right off. Judging by the setup, I think so. Yep. The cap has vanished. Yeah, it absolutely vanished. So you tape the cork to the bottom. I did not tape the cork to the bottom. Okay, actually, I need to explain this. So in the video, you should have seen some tape on top of the cork. So I only did this because this actually is a good example. If you guys look at this cork, there's a hole going right through the cork. That's not good, because if there's a hole going through, then that means that the pressure is never going to get trapped in the bottle. It's always going to escape through the hole, right? So we want to make sure that our cork has no escape. So I just taped the top of the cork so that I can keep the pressure inside, and I just forced it down. So that's why you saw the tape. Boom. Yeah, it really did explode. Abrar, can I use a plastic bottle? You can use a plastic bottle. You can use anything. I just use glass because it's more convenient and I like the way these bottles look. But you can do about anything. Arya, how fast can the cork go? Arnav, I like your response really fast. There's no way I can quantify this in numbers, but depending on like
Do you have a speedometer or something that the cops use to check if you're speeding?
You know what? Maybe I should get one of those, and then maybe we can run this. Abrar said 30 kilometers an hour. That seems fast, but maybe it can. It all depends on your setup, right? Like if you have like a really big bottle, a lot of vinegar, and a lot of baking soda, and most importantly, if you have a really small nozzle, because the smaller the nozzle, the more the pressure, right? The less area you have, the more pressure you have. So if you have a big enough cork and setup and everything, you can get this to be really pressurized, and that could cause the cork to go boom. Can you use this to get to space? You cannot use this to get to space for one fundamental reason, and that's that you can't this one singular explosion will not be enough to get you to space. Like maybe if you had this on a super duper large scale and you had like tons and tons, like literally tons as in like thousands and thousands of kilograms, like millions and millions of kilograms of baking soda and vinegar, and like hundreds of thousands of PSI, then you could probably cause like a reaction big enough to get you like kilometers up in the sky. Like you could probably, yeah, maybe, but you could not stay in space, because in order to stay in space, you need to form an orbit around the Earth, which would mean that you would need to have some sort of continuous burn. But maybe Mark Rover would be like, yeah, maybe Mark Rover would try that. Maybe we should go flood his comment section right now and ask him to make a baking soda vinegar rocket that's powerful enough to get to like 100 kilometers. The cork would burn up. The cork would not burn up actually, because the cork would be abandoned at the very bottom, right? Like once the cork goes out, it's on the ground now, so the cork would not burn up. But yeah. I have a speedometer outside my house. Okay, Abrar, maybe you can use your speedometer and you can test out how fast this cork goes. That's a good idea. And also be known, guys, that like you don't have to limit this to now. So in this workshop, we're going to be making the engine, but after the workshop is over, feel free to take this outside and try to launch the rocket. So like if you want to launch the rocket, you're going to need some sort of pencils or wooden dowels. So I would just use 3 pencils. So put 1 here, and then maybe you could settle with 2, but you just put some pencils on the side like this so that it can stand on the ground, right? So if this is the ground here, if this is the ground, your rocket would stand like this, and then you would just put the cork. So you would have to put everything inside really quickly, and then stick it in the ground like so, and then the cork would eventually pop off to the ground. And this is just how your rocket works. So the cork goes towards the ground. So Newton's third law, right? Equal and opposite reaction. So your rocket's going to move up, right? So you're going to send the cork and all that thrust force downwards, and that's going to cause this rocket to move up. So you could actually make a rocket out of this. Excuse me. So now we have some time. So why doesn't everyone? Let's all go and gather our materials, because I don't want to eat into your lunchtime. So if we get our materials ready now, directly after the lunch, we can just start by putting this together. It's actually really simple to put together. There's not very many steps, but I want to try running this multiple times. So the way this works is I want to try to add some modifications. So number 1 is change the overall amount of baking soda and vinegar. So maybe use a little bit more, a little bit less, and also change the ratio of baking powder to vinegar. So Abrar, is baking soda fuel? It can be used as fuel, but it is not fuel by itself. But you can make a solid fuel out of baking soda or baking powder and a couple of other ingredients, and you can actually light that up, and that would work as a pretty good fuel. It will work as a solid fuel though, because it is a solid and not a liquid. But yeah, so everyone, I guess we're gonna kind of cut 5 minutes early. So everyone, I want you to get your cork, your plastic bottle, your vinegar and baking soda. So someone asked me earlier what the measurement is of each. So there is no exact measurement of baking soda and vinegar. You just
When is the break?
The break is at 12, but I'm gonna let you guys go right about now, because I want you guys to get all your materials ready so that we can start directly right after the lunch. So the lunch starts at 12. So you guys are free to go right now. But if anyone has any questions, feel free to hang back. So Samir asked, what are the plastic cups we use?
Wait, when does the lunch break end?
Lunch break ends at 12:15. Or sorry, wait, not 12.
Okay.
Hold on, let me check the schedule. But yeah, you guys are free to go for a short break right now. And I will bring you guys all back. I want to say, yeah, okay. So the break is, so 12:15, that is right. So the break is for 15 minutes. So you guys have, from now, I'm going to give you guys a 20-minute break. So it's 12 now, 12:15, we start back up again. So 20 minutes, I'm giving you guys 20 minutes of break. And we're going to come back at 12:15.